Hey everyone. All right, let's talk about gravity. So, we've already talked about gravity a bit, right? We talked about how the force of gravity, say, on some objects of mass m is this m times g, and if you drop an object some height above the Earth, it'll fall to the ground at this rate, 9.8 meters per second squared, or little g. I'm going to call this little gravity. Now we're going to go on to big gravity, which is the kind of gravity that we're referring to when we're talking about, say, the force that the force on the moon by the Earth, right, and the force that the moon exerts on the Earth as well, in the opposite direction. Of course, these two, because of Newton's third law, will be equal and opposite to one another, right? That will be equal to minus that. This is the kind of gravity that we're going to be talking about now in Chapter 6. We talk about Newton's law of universal gravitation. So, before we get to that, let's talk a bit about something you already know, projectile motion. So, this problem I call the problem of the headless cannonballer. So let's say that there's a cannonballer. That's somebody who shoots a cannonball is a cannonballer. There's a cannonballer who's very proud of his skills. He can hit any target from any place at any time. He can hit any target. He's very arrogant, and he's confident that no matter where, no matter what you pick out, any location, any target anywhere, he can always hit it. And somebody gets fed up with his arrogance one day and says, I bet I have a target you cannot hit. And he says, there is absolutely no way that you could come up with any target that I could not hit. I will bet my life on it. And the person says, I will bet that you cannot hit the back of your own head. And the cannonballer says, well, that sounds like a difficult shot, but here we have to talk about projectile motion in a little bit bigger scheme, right? It would technically be possible for him to shoot a cannonball, have it go all the way around the Earth, and then strike him in the back of the head eventually, sometime later. Now, the problem of the headless cannonballer is, how long does the cannonballer have to live after he fires this shot, assuming that the shot succeeds? Now, just think about it for a second. Try to come up with like a order of magnitude guess in your head. Do you think it's like 10 seconds? Is it a day? Somewhere in between? Just think about it for a second. Come up with a guess. All right. Well, we can do this problem so long as we know some properties that are going to be important for us. So this is this information here comes from the inside cover of your textbook. You can find it there. It'll be helpful for your homework. I also, at least in my sections, I post a PDF of these things that are on the inside cover of your textbook in case you need them. If you have a PDF of the textbook, it is not included in that. So you'll want to look on the course Canvas page to find that. But if you do have a textbook, it's on the inside cover pages, and the e-text has it as well. So let's just talk about, so we talked a bit about just projectile motion. Now let's talk about circular motion. So you might remember that if you have an object in uniform circular motion, we'll just assume that the cannonball would be in uniform circular motion. It's like it's a perfect shot. If the guy's 6 feet tall, and he shoots the cannonball from a height of 6 feet, it travels all the way around the Earth, never going more than, say, 6 feet off of the surface of the Earth. And of course, as it's going around, right, you might think, well, yeah, but that acceleration's in the y direction or the minus y direction, right? It won't be accelerating in that direction when it's over here. But remember, the minus y direction here would be different because, in fact, gravity is not always accelerating, down in the minus y direction in terms of this setup. With these coordinates in this coordinate system, the better way to think about it is that the gravitational acceleration vector is always pointing radially inwards. So if I set up this unit vector here, and we'll use this notation a lot, to be a radial unit vector pointing out from the center of the Earth, then the rate of acceleration of the cannonball will be this, the constant g in the minus r hat direction. So it's always going to be accelerating inwards. That's exactly what a centripetal acceleration is, right? It's a center-pointing acceleration. So we can use the things that we know about uniform circular motion. So in the uniform circular motion chapter, we learned some important things like that centripetal acceleration, or it also calls it radial acceleration, centripetal is equal to v squared over r. And you already probably knew that velocity, right, is distance over time. So here, here the distance would be 2 pi r, the total distance that it takes to go around a circle, and that happens in a time span of 1 period, and the period is t there. So these two things here, right, nothing to do with this particular problem. This is just for any uniform circular motion. And I can put these two things together then, and I'll get that the centripetal acceleration is equal to, right, 2 pi r over t squared 1 over r, right? Or in other words, it's 4 pi squared r over t squared. Okay. So this is true for any object in uniform circular motion. Now I can start plugging in numbers. Now, if the thing is going around, say, at 6 feet above the ground or something like that, then that height above the surface of the Earth is basically negligible as the thing is traveling around, right? Because the radius of the Earth is 6.4 times 10 to the 3 kilometers, so that 6 feet is entirely negligible. And so I know r then, and the centripetal acceleration is just this inward pointing vector of magnitude 9.8 meters per second squared. So I would have, in the case of our problem, g is equal to 4 pi squared times the radius of the Earth, right, over t squared. Or, in other words, the period, the time it would take for the cannonball to go around and hit the cannonballer in the back of the head is going to be t equals square root of 4 pi squared radius of the Earth over g. Right, it's just multiplying by t squared on both sides, and then taking and dividing by g on both sides, and then taking the square root. Or, in other words, it's 2 pi root radius of the Earth over g. So if you plug in numbers, if you plug in 6.4 times 10 to the 6th meters for the radius of the Earth and 9.8 meters per second squared for g, you get that t is about 1.4 hours. So how long does the cannonballer have to live, assuming he makes the shot that he claims he can make, hitting himself in the back of the head? He's got about 1.5 hours to live. Interesting. Interesting and morbid. Okay, so we talked about this orbiting cannonball thing. What does this have to do with Newton's law of universal gravitation? It has a lot to do with it, actually. When you think about the line of reasoning that Newton went through in order to come up with this idea, he thought of what would it be like if the moon was just kind of like this cannonball. The moon is traveling around the Earth, and it's a lot farther away than the cannonball is, but fundamentally they're both objects in uniform circular motion. And this equation that I derived over here, the acceleration for an object in uniform circular motion, applies to both of them. And so the cannonball was traveling, say, at a radius about the Earth's radius. The moon's a lot farther away than that, and Newton knew that the distance from the center of the Earth to the moon is about 60 times larger than the distance from the center of the Earth out to the surface. This was known. Aristarchus measured this. He was an ancient Greek natural philosopher, and Newton knew all about that. So when he was formulating his law of universal gravitation, he took this into account. So he, noting that the centripetal acceleration, say, of a projectile that's really close would be about g, he tried to think about how this would look for the moon, say, as the moon is going around in a circle that's just 60 times larger. Now, the centripetal acceleration of the moon would be would follow the same pattern, right? The period of the moon is about 27.3 days. That's originally this is supposed to be what a month was supposed to measure, the amount of time it takes for the moon to go around the Earth, but it turns out to not be very convenient that the moon there's not a good ratio of the number of times the moon goes around the Earth to the number of times the Earth goes around the sun. This is another much older scientific problem that goes back a very long time. So anyway, the period of the moon is about 27.3 days. So you can stick that in to this equation here, and you can find out that the centripetal acceleration of the moon is about 1/3,600th of the freefall acceleration g. So that's interesting. Notice, right, that this ratio here was 1/60, and this answer that we came up with for the centripetal acceleration of the moon is about 1/60 squared. So this could be a coincidence. There's a lot of examples of crazy coincidences coming up in ratios and things like that in science that has derailed people and led them on wild goose chases. The ratio of the proton mass to the neutron mass and things like that. But Newton thought, well, maybe there really is something to this. So maybe the force of gravity is proportional to 1 over the distance squared. So the gravitational force attracting two bodies together might fall off like the distance squared. That was hypothesis number 1. Now, on to the next thing. He had a few other hypotheses. So one was based on this observation that you've already seen in the lab, right? That objects fall at this rate, little g. And objects fall that way, whether they're heavy objects with large mass or lighter objects with less mass, they all fall at the same rate in free fall in the absence of air resistance. So given that the force of gravity is on some object is, say, the mass of the object times the acceleration. The acceleration in this case would be g, right? Or in other words, rearranging the equation, the acceleration would be the gravitational force divided by the mass. Well, if A, the acceleration, is independent of mass, then that means the force of gravity over the mass would be independent of mass. Or in other words, the force of gravity has to be proportional to the mass, right? This can't be independent of mass unless the numerator is proportional to mass, the mass of the object. So that was hypothesis number 2, that the gravitational force might be proportional to the mass of an object. Now, notice, right, that what's really causing this gravitational force is the Earth, right? It's the gravitational influence of the Earth at that location of the massive object that brings about this force, the force on the object by the Earth here. Now, if the force on an object by the Earth is equal and opposite to the force on an object, the force on the Earth by the object, as we know to be the case from Newton's third law, then if the gravitational force is proportional to the mass of an object, the mass of the object, then it must also be proportional to the mass of the Earth, right? There's a symmetry here. The gravitational force can't be proportional to one mass differently, to a different power than the other mass, because both masses will enter into these equations in the same way. So that then is hypothesis number 3, right? That the force of gravity on the object would be proportional to not only the mass of the object, but also the mass of the Earth. Now, putting all 3 of these things together, that the gravitational force on an object would be proportional to 1 over the distance squared, it would be proportional to the mass of the object, and it would also be proportional to the mass of the Earth. You can put those together to get that the force on an object by the Earth would be proportional to the product of the masses divided by the distance between the 2 of them squared. And this, by the way, is the distance from the object to the center of mass of the Earth. The center of mass of the Earth, so not the Earth's surface. Okay, now if you then want an equality instead of a proportionality, you can introduce some constant of proportionality. We now call this Newton's constant, and it's big G. So there's 2 gravitational constants. There's little g, 9.8 meters per second squared, and then there's big G, which is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. That one's a little harder to remember. So stick that in there, and you'll see that the force on an object by the Earth is G, big G, times the product of the masses divided by the distance between the 2 of them squared. And what makes this universal, by the way, Newton's hypotheses turn out to be correct. These are all correct. And lastly, I should point out that what makes this law a universal law of gravitation is that that all masses, all of them, pull on each other in exactly this form. So there's nothing special here about the Earth, of course. Everything attracts, everything with mass attracts everything else that has mass in exactly this form. So here I have the force that is exerted on the moon by the Earth, right, pulls the moon in this way. The moon pulls back on the Earth in an equal and opposite direction. The same thing happens with that tiny object. That tiny object is pulled down by the Earth, and that object, sure enough, as imperceptible as an effect as it actually has, will bring about a force on the Earth that comes from that object. And of course I could also include here, right, there's going to be a force on the moon by that object, and a force on the object by the moon as well, because everything with mass attracts everything else with mass.